So welcome to this session. The whole idea behind this session is that when you're troubleshooting complex problems, you often need to be thinking concurrently about both what's happening on the sender and what's happening on the receiver. So I put this course together to try to drill down into some examples of what do you see when you're looking at one side versus the other, to help you kind of compare and contrast and infer. You know, if I'm looking at a client side, why do I see what I see, and what might be happening on the sender side if I'm looking at the receiver. So we're going to drill down into lots of very interesting examples with one capture. And while I was doing my research, just as fate would have it, I did some Googling, and I found out that this is not just a TCP thing, this concept of a split brain. Apparently, it's also a mental, potentially a mental thing. So in terms of your agenda, why you are here this morning and why you chose this session, hopefully it's because you want to fine-tune your Wireshark skills. You want to fine-tune your TCP understanding and your TCP skills, learn more about what you should expect to see or what you can expect to see when you're looking at a sender versus a receiver capture. And then overall, taking all of this knowledge and taking your troubleshooting skills to the next level. So my agenda, what I plan to talk about, is we're going to compare and contrast TCP endpoint behavior in a number of different scenarios. I'm going to drill down to what do we see and why do we see that. And I'll be hopefully interacting, asking you guys to comment and participate, certainly questions. We're going to promote a bunch of Wireshark features. We're going to share experience and ideas. And I'm also going to expose you to some visualizations in a tool outside of Wireshark to help cement some of the concepts that we see inside of Wireshark. So if you saw me yesterday, you know my story. I love troubleshooting. Been doing it a long time, and I shaved my beard off in 2003. But a few additional details that you might not have heard about from yesterday. One of my favorite quotes is here. And my goal today is to stimulate your thinking, not to just fill up the pail with information. I mean, there's going to be a lot of information, but I really am hopeful that it triggers more curiosity, it triggers more introspection. That's my goal. That's what I'm hoping for. A favorite book of mine, it doesn't really show well on the graphic. It's called Wisdom Without Answers. So depending on what questions you guys have for me, I might refer you to the book, if that's okay. All right. So my ask of you guys, I'm hopeful that you'll engage, participate. We've got a lot of really detailed, like microscopic level material to look at. And we're going to look at things that honestly don't make sense. It's like, wait a minute, how could this be happening? Why could we have this condition given what we're seeing? There will be some things that are confusing and possibly contradictory, so I'm going to ask you, please ask questions and please question answers. To the extent that we can, we'll drill down in more details. It's a lot of material. The time's going to go by really fast. I have kind of given myself a little bit of a time schedule of where I need to be at certain time points, so I may need to speed up or say that we have to move on at certain times. But I'm absolutely available the afternoon and during lunch as well. And I put those spectacles up there because if you wear glasses, as for what we're looking at, your glasses might need glasses. I mean, we're going to look at some really detailed material and maybe through different lenses as well. So for this session, I created the material with Wireshark 2.6.3. I know that's not the latest, and I wasn't able to update it in time for this session, but I did take a snapshot using 3.0.1, I think it was, and there wasn't a lot different other than 3.0.1 was a lot faster loading captures in terms of the content that was on the screen. There's some pre-filtered endpoint capture files for a specific connection. So this was pre-filtered ahead of time, and we'll be looking at just one connection between two hosts. Then I'll give you more background about the application in just a second. There'll be some Wireshark profiles we're going to look at and share. Those will get uploaded to the conference site after the conference is over. And we're going to be using some examples of a riverbed tool called Transaction Analyzer. That's the last time I'm going to mention the name of that product, because this is not a sales pitch. This is a technical deep dive. If you decide you want more information afterwards, please see me. But we're going to be looking at some visualization and some advanced analytics from that tool. So part one, so this is a two-part session. Part one, we're going to quickly go through the background on the application that we're going to troubleshoot and that we'll be reviewing with Wireshark. We'll look at the topology and the symptoms that we're trying to troubleshoot. And then we're going to start our compare and contrast. What do we see on the sender? What do we see on the receiver for the same conversation? In part one, we're going to start easy. We're going to start gentle with the three-way handshake, latency, TCP state. We're going to drill down into expert info, comparing and contrasting. And then from there, we're going to deep dive into fragment overlaps, out-of-sequence retransmissions, and some SSL errors that show up in the expert info. That's for part one. For part two, after a break, we're going to continue basically where we left off. And then we're going to drill down into bytes in flight. We're going to drill down into round trip time to ACK. And then we're going to end up with latency versus congestion. What is it? How do you measure it? What's the impact on performance? And how do you interpret it when you're looking at both sides of a connection? And then we're going to wrap up. So that's what we're going to cover. Let's get started. It's go time. So here's our troubleshooting scenario. We're going to be looking at an HTTPS web application. The private key, unfortunately, is not available. So we're going to be working with layer 4 SSL as our analysis point. We're not able to see into the HTTP layer. And the host-based captures were taken on my laptop and on a web server that I was using at the time, where I was getting insanely bad performance. So here's the symptoms that we're going to analyze as we go through our compare and contrast. So downloading files takes forever. I imagine you guys hear that a lot. People come to you and they go, "Man, it's so slow. What's wrong with your network? It takes forever." Well, that's what was happening here. It was taking forever. In fact, it was taking 16 seconds, which really felt like forever to me because I was in a hurry. I was actually in the middle of troubleshooting something and I needed a capture file and I was trying to download that capture file. So there's one TCP connection out of thousands that were active at the time. I'm at home with my laptop. I probably got Pandora on. There's music playing. There's Outlook doing stuff in the background. There's tons of traffic on my capture, tons of traffic on the server capture. All of that's been filtered out, and we're going to focus on one specific connection, 52942. So in terms of the topology, it always helps to understand what's in between the client and the server. You know, what infrastructure is there between? So it's a very simple topology, right? It's my laptop. I'm in Orlando. The server is in San Francisco someplace. I've got an IP address. They've got an IP address. What could be simpler, right? Unfortunately, the reality is I've got wireless in my office that I manage. I don't know what version it's running. It could be old. It's not new, I know that. I hop onto my ISP. I've got to go up to a VPN concentrator in New York, going through some number of internet hops, who knows how many. And then from that, I'm going to try out my pointer here. Let's see. Look at that. Okay, look at that. Is that not nice? Then from this VPN concentrator, we've got to jump over to a VPN gateway in San Francisco, going through who knows how many ISPs, transit ASs, et cetera, to get to the web server in San Francisco. So we've got a number of protocols involved. Honestly, I'm not sure if I'm doing IPsec up to New York or if it's SSL, to be honest with you, I don't remember. But we've got that translation. We've got a lot going on for me to talk to the web server in San Francisco. But that's the topology at a high level of what we're dealing with. And it's time for our first pop quiz. Are you guys ready? Okay, first pop quiz. And if you know the answer to this, please don't shout it out. Just raise your hand. What parking slot number is the car in? Can you do the math? We got one hand up. It's complicated, right? Somebody gave this to me. I go, hell, I don't know. That doesn't make any sense. The gentleman in the back.
It's 87.
Thank you, sir. Because if we flip this around and we change our perspective, right? And it's all about perspective when we're talking about what the client sees or the sender and what does the receiver see. It's all about which direction you're facing when you're doing your analysis. Like, what am I going to see in the capture? So I thought this was a good way to kick off the discussion around we're going to compare and contrast and see things from different perspectives and try to do the analysis. So it turns out that each endpoint does have a unique perspective. And each endpoint is independent. They do make decisions on their own, but yet they're influenced by what they get from the other side. So you've got this combination of independent acting and independent behavior mixed with adapting to what the other side is doing, as observed through acts and payload coming between sessions. And of course, third-party actors can have an effect on behavior. You could see from my topology, I've got VPN concentrators. I'm going from Wi-Fi to Ethernet to go out to my cable provider. I mean, there's a lot of third-party actors involved in my connection. So the key point is each endpoint has its own perspective. And that's really the premise of what we're going to be drilling into for these two sessions. So we're ready to split brain. Left brain is the receiver, right brain is the other host. We're going to start again very gently with three-way handshakes, and then we're going to kind of introduce more complexity. As we get down to the bottom, we'll definitely be into the weeds, but we're going to start nice and easy with a three-way handshake. So let's take a look at that. So in a lot of the screens, you're going to see an arrow pointing to the file name to help us remember what are we looking at the time. So when you see client up here, that's the client-side capture, and you'll see server for server-side capture coming up. So starting with three-way handshake, I'm confident everyone here in the room is familiar with the three-way handshake. But what's interesting about it is what gets negotiated and what gets declared at the TCP level for inside the three-way handshake. And these details are always important to have for troubleshooting if you can have them. Sometimes you can't capture the three-way handshake. But when you can capture it, it gives you really important information. Like in this case, we're looking at segment size, we're looking at whether or not SAC is permitted, and window scaling. So we can see the client has said something interesting, which is, hey, maximum segment size 1360. And what we're going to see in a minute on the server side is, to the extent that it's interesting or important, its segment size is different. So already, even with something as simple as just looking at the three-way handshake, we can see each side has a different perspective of how much data can move in each direction at one time in terms of maximum segment size. So we've just completed our first comparison, right? Yay, we finished. This is going to be like a relay race or a marathon or a triathlon. We're going to be trying to take small segments, looking at some differences each step of the way. The easy one is done. This was the warm-up. The next one's a little bit easy as well. But before we go on, is everyone comfortable with the TCP options that get negotiated at setup time? Okay. There's one that wasn't shown there. What's one that could also be negotiated that we didn't see? Say it again, please. So scaling is there. Oh, sorry, let me fix that for you, because wait until you see what this pointer does. Look at that. But I forgot which one you said. Oh, scaling. Yeah, so scaling is there. Window scale. Say it again. Timestamp. Yep, perfect, exactly. All right. So we finished our first comparison. Easy peasy, we're feeling good. It's like, that didn't hurt too bad. Let's keep going. So now let's take a look at what each side thinks about latency. So we're going to do side-by-side comparison on the top, up here. On the top up here, we've got our client. Bottom down here, we've got our server. So we can tell from Wireshark, and looking at the three-way handshake from each perspective, what latency was at the time, and this is really a key point, at the specific time that the handshake took place, right? So we can see the client capture. We can tell from looking at the time deltas that the latency, the round trip time, was 121 milliseconds from the client's perspective and 129 milliseconds from the perspective of the server. Now, there's not a lot of difference there. It's 8 milliseconds. But just thinking out loud, what are some of the reasons why you would see any difference? Sorry? Say it, I'm sorry. Oh, asymmetric routing. That could be a reason. They're taking different paths, right? But processing on each endpoint, that could play a factor, absolutely. My server's on an ESX host that's oversubscribed. Because, how do I know that? Because all ESX servers are oversubscribed, right? Even when we're told they're not. Actually, that's not true. I have seen some very disciplined customers that don't oversubscribe, and they're really very disciplined about it. And in those environments, it works absolutely great. Okay, so we said asymmetric routing, host could be busy, and just the fact that in terms of minute time, there is a difference of what was happening along the path between each direction, and it could just be congestion, minute little, and we're going to drill into that in part 2. But already we can see some differences. Yes, sir.
S plus in the info field on the bottom.
I might have to give you my pointer.
In the info field of the capture on the bottom, there's an S plus at the beginning before the port numbers.
I don't know for sure. I think it's because I squashed things. I think it might be a function of the column size. Yeah, but it's a sin. Yeah. Okay, so here's something exciting. There's a steelhead in the path. And for those who don't know steelhead, thank you for that. It's a WAN accelerator. So what I didn't see, though, is I didn't see in the options anything that said riverbed, which sometimes we do see. And by the way, I'm not expecting to have steelhead in the path because I didn't have steelhead enabled. So, okay, but it's a great question. Okay, so we can see where the time differences are being measured. Does it make sense to everyone that we're taking our measurement at the top in the second packet, and we're taking our measurement in the bottom in the third packet? Does that make sense for everyone? Excellent. And within Wireshark, there is a computed field called initial round trip time, IRTT, which I believe is around and available for the life of the connection. So if you ever needed to go back and say, if you're like, I'll make up a number, 5 minutes into a connection, and you're looking at response times and other details, you'd be able to be reminded what was the initial round trip time during connection setup. So that's a useful field as well. And when you see things in brackets like this, what is that telling you when you see things in brackets? That it's a calculated or derived field by Wireshark, exactly. And there's a lot of really great additional derived fields that Wireshark provides. So whenever you see that, definitely make use of it. And we're done with our second comparison. So again, not too hard yet, right? We still got energy. Nothing hurts yet. So what we're going to do now is we're going to look at, with Wireshark, we're looking in, the way I describe it, we're looking in 2 dimensions. We're looking at a list of packets. But what if we could actually visualize the traffic bouncing between hosts, and we could see things like frequency of transfer, density, how close are the messages together over time, how long do things last over time? What if there was some additional analytics overlaid on top of that visualization that helped guide you towards the next rock to look under? That would be pretty useful. I think most people would agree. If only there was such a capability. Aha, but there is. So we're going to look at this viewer, and at a couple different points during these sessions, we're going to use this view to help us kind of get some perspective of what's happening at the other end while we're looking at what's happening on the end that we're seeing. So some quick orientation of this view. The first thing to note is we've got time moving from left to right. So there's a time scale in elapsed seconds. There's a swim lane box that actually is where traffic moves between hosts. So if we start here in the left-hand corner, we have something leaving the top of the swim lane, traveling down to the bottom, bouncing off, coming back, bouncing off, coming back. So we use that swim lane to visualize things, traffic moving across the infrastructure over time. And the slope of that line gives you a sense of how long did it take to move. We've got our IPs that are talking to each other. So in the very top of the swim lane's the client, the very bottom is the server. And then based on what you select, if you pick an arrow or multiple arrows in the swim lane, then you get decode summary at the bottom telling you what's in that arrow. And this will become useful in just a moment. Now that we've got some orientation, one more item on orientation. In Wireshark, we get one time value captured, and that's the timestamp of when the packet either came into the NIC or when the packet left the NIC. In this viewer, we're able to provide 2 times. One time is the truth, which is when a packet either left or came in, and the other time is an estimated time based on latency. And we use that estimated time to calculate the slopes. So let me talk a little bit more about that, and then we're going to get into some specific examples. So every capture has the actual time that something happened. Either a packet came in or a packet went out. And we can use that information with latency. We can add latency to it and do a pretty decent job of estimating either when it left the other side or when it's going to get to the other side. And let me show you some examples of that. So here we're looking at the client capture, which is the top part of the swim lane. And the arrows that I've circled in purple, those are the actuals for sure, because they were measured on the client. There's no question about it. That's the time when things actually happened. Either a packet left on the left-hand side, or a packet arrived and another packet transmitted on the right-hand purple side. So using those details of what things actually happened, we can then estimate the other end, right? So if I know when something left up here, I can add latency to that, or at least our best understanding of latency, like initial round trip time. I can add latency to that and predict when it got to the other end. And likewise, when something arrives here, like the arrowhead, the red arrowhead, when it arrived here, I can predict when it left the other end. And now what we can visually see is sort of both ends at the same time in one view. And that'll be useful for some examples that we're going to look at coming up.
The predictions, are they only based on IRTT or is it something more sophisticated?
So there's an algorithm where we look for the lowest observed round trip time. And we use that lowest observed round trip time as the best information that's available, right? And then we adjust accordingly when this view is produced. Okay, so we're going to now take that visualization model where we can see things on both endpoints, and we're going to apply that to TCP state, because I want to make sure we're all comfortable with TCP state as it relates to what's happening on the sender and the receiver. So let's get started with an overview. Hopefully everyone is comfortable with the state definition for TCP. At least when we start up a connection, starting at row 2. Well, row 1, nothing has opened yet on one end. The other end is listening, waiting for a connection. Then somebody sends a SYN. The SYN gets received. One side says it's established. The other side says, well, I've received the SYN. Then they agree to both be established, and now we can transmit data. Is this something familiar to everyone, this state model? Because it's a really important information about TCP, knowing, number one, that there is state, and what that state is and what it can be depending on circumstances. There's also a state mapping for closing down sessions. I don't have that here, but just be aware of that. And if you're not familiar with it, you can refer to the RFC. But it's also very useful information. So we're now going to kind of test some understanding using this visualization.
Is the transaction analyzer part of the Wireshark?
It's sort of the other way around. So we have to have Wireshark in order to get Transaction Analyzer to work. Yeah. But I want to hold on, to the extent that we can, let's, after the session, if there's more questions specifically about that, because I want to focus on Wireshark with some supplemental visuals to help support things. So now that we can kind of see both ends at the same time using this visual, I've got a couple of questions to walk through, kind of a pop quiz. So we've got a point in time with our timer, and my question is, given that very specific point in time, like right here, what's the current state? What's the TCP state of each host? So we want to think in terms of what does one side believe the state is? What does the other side believe the state is at that specific point in time? So I've got listen on the receiver, right? And SYN sent. So let's see. Perfect. So now we're going to move forward in time and test that theory some more. So now we've moved forward in time, and we want to ask the same question. So we've got SYN sent at the top, sent, and SYN received at the bottom. Let's see if that's right. Everybody comfortable with that? All right. So at this point in time, in the last one, they don't agree on state because we're in the middle of trying to establish a connection. Okay. What if we move our time point this way? Now what do we have? Say it again. On the client, on the sender, what do we have? Established and SYN received, right? So we haven't changed state, have not changed state on the bottom because really nothing, we don't know about anything else that's happened from the bottom perspective, but on the top, we've received the SYN ACK and we've sent the ACK and now we're ready. We believe the session is established. Let's keep moving forward in time. Anything different? Still the same state? Good. And this one I want to zoom into a little bit. Notice our time is right in between the green and the red. So what do we have now? Established, established, good. And then my question is, what would happen if the green arrived before the red? Hypothetically, there was a network issue. And the green arrived before the red. What do you think would happen? Say it again? No, if the green line, which is the data, so I didn't point out, so the green visually says there's payload. Right, and what happened in the client side is we completed the handshake and we immediately sent some data. But on the receiver, hypothetically, what would happen if green arrived first? Well, our session is not established yet, right? So we'd have to say, well, I can't do anything with this because there's no session. I'm in a SYN receive state. So either, and I think it's going to depend on the stack, either I'm going to have to respond with a reset because we're out of sync. In fact, I think that's the only option. But just hypothetically, I wanted to bring that up. And then now in this state, established. So we're fully open now at this state. Now, this is kind of hard to do if you're comparing two decode summaries on the same screen, at least for me. I'm a visual person. So being able to see what's happening kind of globally at both ends, for me, is very useful. And I want to ask you guys, do you currently think about the other side? When you're doing troubleshooting and you see a condition, do you think to yourselves, what was actually going on? If I know what latency is, what might have been going on at the other side? Is that something you think about today? Is there a question in the back?
Yes. In the real world scenario, is it possible to see the green, the payload before the transaction completes, QA actually completes?
So the question is, in a real world, would it be possible for the green to show up before the red? Yeah. Anybody want to take an answer to that? The answer is yeah, because it's anything can happen, right? Things can get out of sequence. We did a session yesterday on that. Yes, sir?
But when do you see that in the capture? You said that in the first three packets in the three-way handshakes, would you not see that you had a payload in between maybe the second and the third?
So your question is, wouldn't you see that in the capture? And that's a perfect question. That's part of everything, that's our premise for this entire session. And it depends on which capture you're looking at, right? So if you're looking at the client, everything looks great, but the server's sending a reset. Why did he send a reset? If you're looking at the server, you're seeing things arrive out of order, and he's like, no wonder we sent a reset, right? So that's the split brain kind of, always be thinking about what does the other side see, yeah? And do you think about state? And literally, we're still just getting started, okay? And we're finished with our third. It really gets insanely complicated from here, which is why I wanted to start slow. Okay, so next we're going to drill down into Wireshark expert info summary for each capture. And let's see what that looks like. So we're gonna compare side by side the client, which is this screen, and the server, which is this screen, and we're just going to put them visually side by side with each other on this side. So the server is the left count, and the client is the right-hand side count. And you can see that most things are very different, with a few exceptions. And we're going to drill into these as part of our exercise. It's like, okay, expert info found things, it did its job, which is to help us learn what maybe is not healthy or error conditions or warning conditions in each capture. And because expert info is looking at different sides, independently it's coming up with different counts. And we're going to examine these different counts. So let's start with retransmissions. So I've got a couple of questions. So you can see with retransmissions, server says, hey, I've had 15 fast and 15 not fast. And the client said, I've got 4 and I've got 5. So why does the server report more retransmissions than the client? Well, so your point was because the client hasn't acted the data, right? So I think it's helpful to make sure we understand what do we mean by retransmission. When expert info flags something as a retransmission, what does that mean? How did it come up with that flag, that designation? So I want to make sure I bring up this help screen because honestly, when I first started using Wireshark, I can't promise you that I spent a lot of time in the help subsystem. But I want you to know there is a help subsystem, and there's some really good content there that the developers put in, right, that help explain things that are happening. So here's the definition, not of a retransmission, but of a fast retransmission. So if expert info is going to flag something as a fast retransmission, there's the conditions that qualify for a fast retransmission, and there's 6 of them. And then what's really interesting is down here, I'm trying to change my pointer so it doesn't magnify. To do that, I'm supposed to double click, so let's see if I can do that fast. Did it, okay. So now instead of a zoom in, it's a highlight. Is that cool or what? I love this thing. Yeah, so notice it says supersedes, out of order, can anybody say that? Spurious? And retransmission. So there's a hierarchy of conditions for expert info, and we'll be spending some time talking about some of the results of that hierarchy, but you can see that fast it's like I was going to say trump card, I shouldn't do that. Fast retransmission takes precedence over those bottom 3, right? So you could have something that at first looks like out of order, but then it gets elevated to a fast retransmission because of the conditions that are being evaluated. So let's keep going. We're going to look at some more definitions. So we did retransmissions. We saw they were different. We talked about why they're different. We didn't talk enough about why, sorry. So using this help screen, the reason they're flagged as retransmissions on the server is because Wireshark saw the same segment twice on the server. And when you see the same thing twice, we think it's a retransmission. The client did not see the same segment twice because it got dropped. The first one got dropped. So that's why it's not a retransmission on the client side. Does that make sense? Peter?
Segment or the same sequence number?
Well, good question. So when I'm saying segment, what I'm implying is that block of stream bytes starting with the same sequence number. They could be different sizes. And yet, even with overlap, and we're going to look at overlap in a minute, they can be different sizes, yeah. Okay, let's talk about out of sequence and drops. So there's huge differences here. We have at the top, the frame is suspected out of order. Does that show up for the people in the back? If you squint? Okay. So here we have a case where the client says, I've got more of these conditions than the server does. It's the opposite of retransmission. So question, why does the client report more out of sequence and previous segment not captured?
Something happened on the way to back to travel from the server to the client, somewhere along the way.
There was packet loss. So there was packet loss and reordering of packets, both of those things occurring. Make sense? Why we don't see that on the server side? We do see some on the server side, and we're going to drill into those in a little while. But the majority are showing up on the receiver, which, I put client and server. I probably should have put sender and receiver. Okay, and we're going to drill into this question in a little in part 2. Like, why does the server report any of the stuff he's sending as out of order? It's like, how does that happen? So we're going to drill into that in part 2. So here's the definition of out of order, and notice that it also supersedes some things. It supersedes spurious, and I can't say that word, and supersedes retransmission as well. So think of the expert info system as a list of rules with conditions, and when those certain conditions or combinations of conditions are encountered, then we flag the packet with that either error or warning, etc. So far we know, geez, the server says there's a lot of retransmissions on this connection. The client says there's a lot of packet loss and out-of-sequence packets on this connection. So they're both kind of saying the same thing, but they're saying it in different ways based on their perspective, their point of view, one being the sender, one being the receiver. So let's keep going. We had this warning in expert info saying, hey, I've got some SSL, but I don't know what the heck it is. I can't figure it out. I can't decode it. And the client said, man, I had 128 packets flagged like this, and the server said I had 8. So my question is, why does the client report more SSL unknown records than the server? I mean, it's quite a difference. Anybody, think about what we already know. There's packet loss and there's out of order. Well, we know we've got an unhealthy network, right? We've got packet loss, we've got out of order. Think about what the SSL engine has to do. If you think about SSL, there's a lot of SSL messages that don't fit into one packet. So there's SSL messages that have to span multiple packets. And then Wireshark has to reassemble those messages. I don't want to call them fragments because they're not IP fragments. They're like portions of the message that it just won't fit into one packet. So it has to be sent in multiple packets. And then Wireshark, the SSL decoder, think of Wireshark as having dozens, if not hundreds, of small modules that do specific work. And SSL reassembly, that's the word I'm looking for, reassembly. I've got to reassemble these messages from many packets into a single message. Does that make sense? Right? It just won't fit into one packet. So as part of that reassembly, if I'm Wireshark SSL reassembler module and I'm trying to reassemble messages as packets come in and there's out-of-sequence packets or there's packets missing, I can't finish my job, right? I'm trying to reassemble, it's like, can't do it, I don't know what this is, it's an unknown record. Does that make sense? So this is a consequence of packet loss and reordering. Any questions about that? It's kind of a key point because we rely on expert info as our co-pilot as we're driving Wireshark. Expert info will say, hey, you've got all these conditions, and it's really up to us to validate that. Yes?
So would the SAC come into play at the SSL level so that you would have the right edge and the left edge, or is that not at the SSL?
So that's a great question, actually, because in theory, I shouldn't be handing anything off to SSL until it's all in order, right? But I think that would be, I love that question even more now. It just triggered an idea. The reason the connection didn't break completely, the reason I was still able to do my work, web client talking to web browser, is because TCP did exactly what you said. It reordered, it maintained proper sequencing, and then delivered it to the SSL layer on my client. So you're absolutely right. But that's not what Wireshark sees. Think about what Wireshark sees. Wireshark sees these packets coming in, and it's trying to reassemble the messages, but Wireshark is not a TCP stack, right? So Wireshark is saying, let me do the best job I can to make sense out of what I've been given. And in this case, it's saying, well, there's unknown records because I can't put things together within the time period. And there may be some improvements in the SSL reordering, resequencing engine in Wireshark. So this is 263. 3.0 might be better. But I did check it with 3.0 and I got the same numbers, right? This is really probably a priority issue for what do developers work on when, right? But this is an area where it needs a little help, I think. Did that help? Yeah? Okay. Yes, sir.
Just a comment, a lot of these warnings like this where something's unknown or can't be reassembled or something like that, a lot of that really depends on your settings that you have in your preferences. And so depending on what you have set or not set, if you're capturing full packets or slicing at the beginning, will have a completely different impact on what you see on the expert input.
Excellent point. So let me repeat what you said for everybody and the recording. So what you said was the preferences that you've set in your profile and in your environment for things like interpreting, reassembling, even dealing with TCP reassembly will affect what you see here. So that's a great point as well. These are all default settings, by the way. So you could make these go away by saying don't reassemble SSL. Yeah. Does that make sense? Okay. So let's see. I think I told you I didn't start by using the help system, and I didn't start by learning profiles. I wish I had, and learning preferences. Because protocol preferences, there's some really great ones that do influence this, so I'm really glad you brought that point up. Yeah. Okay. TLS ciphertext length must not exceed some big number. And this is also from the client. So why does the client report ciphertext length error and the server does not? And the answer is pretty much the same thing we just talked about. We're trying to put things back together again. We're trying to interpret it, but the traffic is too messy, and we're not able to do that. So just another example in expert info. And then I think I already commented on this. So we've identified the issue as not being able to reassemble everything in a timely manner on 263, and maybe with a future version it'll be better. And I think I'll update this slide to say depending on your preferences, like you just pointed out. Yeah. Has everyone seen the protocol preferences in Wireshark? Or maybe I should ask, has anyone not seen it? I mean, it's an extensive list. If you pull it up, you go, oh my God, what's all this stuff? I tend to look at the TCP. I think that's the only thing I've ever messed with is TCP for the most part. Okay, fragment overlap. Why does the server report a fragment overlap error and the client does not? So notice we're in the server side capture. And this is going to be the topic of a deep dive that's coming up momentarily. And we'll also ask the question, should this really be severity of an error? And maybe that might be one of the preferences. I haven't looked to see if we can change the severity. So before we deep dive into fragment overlap, we've looked at a number of differences. Do these differences... Does it make sense now why we see different things on different endpoints? I mean, we're really in a process here of compare and contrast. Any additional thoughts, comments? Is it useful to think, I'm doing left brain, right brain, is it useful to think in terms of what's happening on both ends, and why does one end think one thing and the other end think something else? This is hopefully the lighting the fire as opposed to filling the pail. That's my goal. Okay, so I've summarized what we've discussed. I won't go through all of these. This will be part of the deck, and I'll also upload this spreadsheet. But we've looked at SYN, latency, TCP state. We drill down to several expert info areas, and then there's some notes around what we saw and what's different between the sender and the receiver. And this is in the deck. This will be published up to the website. So we're going to drill into one of these fragment errors because it turns out there's some great additional details to help stimulate more thought. So we're going to drill down, but I thought I had a slide in here, which makes me think, do I have a slide? No, we don't. Okay, so the slide that I put in here, if you guys will humor me, was just to stand up, stretch out a little bit, get your legs going, do some exercises, turn to the right and greet your neighbor, say, hi, my name is, no, wrong meeting, sorry. Does anybody want to just quickly stand up? We've been sitting for an hour almost, and it'd be good just to get the blood flowing, right? Because we're going to be sitting again for another little bit, another half an hour. I mean, I'm doing all the standing, so I should probably sit. Oh, by the way, this wasn't an invitation to leave the room, guys. No, come back. This was just a quick stretch break. Okay. No jumping jacks, no squat thrust. Sorry? No burpees. Okay, so pop quiz. And if you were with me yesterday, don't shout out the answer yet. If you weren't with me yesterday, what's one of the best things about Wireshark? Colors. Haven't heard that one yet. I like that one. Anything else? The conference. Sorry? Extensible. Customizable. Okay, besides the developers. That's the answer I was looking for, you guys. The developers. Think about what these guys do for us. And it's free. I mean, I like to make sure I promote what they do. And they do it, I don't know, this sounds a little corny, they do it out of love, right? Love and passion for the technology and for us as making good use. But then all the other answers that you guys called out. Flexible columns, views, and profiles, colors, all these things are amazingly effective. So if you've not looked at the help system for profiles, it's pretty extensive. It walks you through there's a lot you can actually set as part of a profile, a lot of settings. So be aware of the help. We're going to use some of these in our next drill down. So I will be uploading 3 profiles, one called SAC, one called IPID, and one called sequence analysis. It'll be uploaded after the conference with the PowerPoint and the video and the spreadsheet that I mentioned. Okay, so our goal now is we're going to drill down and understand fragment overlap. What does that mean? How did the expert info decide it needed to call that out? And starting with this classic, so this is the classic profile out of the box Wireshark. It doesn't really give us what I'd like to have in the view to quickly understand the fragment overlap. So what additional columns would you want to put in this view if you're trying to so fragment overlap means I'm seeing one segment that overlaps with another segment, fragment overlap. What columns would you want to see in your view? Sorry? Okay, so bytes and flights and flags. So TCP, like sequence and ACK. Great choice. Great choice. So I was almost with you because ACK is good too. But I chose sequence number and next sequence number. But ACK works as well, totally. But the key for the overlap is looking at the sequence numbers. And it turns out, we have a pop quiz. Before we can drill down further, we have to have another pop quiz. It's a slight diversion. What are jumbo frames? So offload and so anything over 1,500? Yeah, okay. What are super jumbo frames? Have you guys heard of super jumbos? So they're bigger than 9K. Are they real? I don't know. I thought they were. I Googled before the class. I saw some reference to something experimental, but I've seen frames in Wireshark over 9K, and that's the segmentation that it's Peter that Peter mentioned, and we're gonna drill into that a little bit. So when is a jumbo frame not a jumbo frame? And the answer is when segmentation offload or large send offload is enabled. And I needed to cover that because in our sample, we've got all these giant frames, length 2623, 3930. This would be good to magnify. 5207. It's like, wait a minute, how can that be? Now those are legally in the range of jumbo frames, but sometimes you'll see 23K, 32K, I mean insane numbers. And as we look at the fragment overlap, we need to understand this a little bit better. So when we see large frames, and we're pretty confident that jumbo frames are not enabled on the switch, because they have to be enabled on network interfaces to have jumbo frames, then it's most likely something called large send offload, which you can Google. But essentially it means that the application is passing a large buffer down to the NIC card. And the NIC card is going to handle chopping those up into multiple packets. So what Wireshark, and the session this morning, by the way, that was I thought was really good around the capture architecture, part of the questions, or something to understand about this is, when does Wireshark see the packet? What we think of as a packet, when does Wireshark actually see it? And we got a glimpse of that in this morning's keynote with WinPCAP architecture. But it turns out it's coming from the app layer, being sent to the NIC card. We see it going to the NIC card, and then the NIC card takes care of chopping it up into smaller packets. So we just answered some of these questions. It turns out that there's a corollary called large receive offload. So if you're looking at a receive side capture and you see these giant freaking frames coming in, chances are large receive offload is turned on, particularly in a VMware environment. And I have to be honest and tell you, this condition had me spinning my wheels for about 3 weeks, because we were trying to figure out how in the world can these be passed across the network. And at that time, I'd never heard of large receive offload. But it turns out it's at least a VMware thing that helps to optimize what happens inside the ESX host. All right, let's go back to...
Sorry.
Yeah, no worries.
In terms of this, what operating systems are affected by this? It sounds like Windows.
So where I've seen it is in a VMware environment. So the operating system doesn't know. It's just being handed, segments from the VNIC, right?
Regardless of the host.
It's a NIC card dependent. Yeah, I see it on Linux.
Gotcha. Okay.
Linux, you see it's like the IBM AIX.
So you see it on the AIX as well? Okay.
It's whatever the NIC supports.
And on the good news side, what it does is it reduces the amount of packets per second coming into the VM, right? Because we're taking many packets and not coalescing them, aggregating them. Yeah. So I guess if you can save 1 interrupt, you're a hero, right? Or 10 interrupts. Okay, let's go back to fragment overlap. Now that we can understand some of these large TCP lengths that really needed some explanation. So here we can see frame 714 over here, and it's got sequence number 52283. Did I do that right? 835. And that fits somewhere in between these two numbers, 522835. So it's less than that, and it's greater than that. And because I'm a visual person, I need to see a picture of what that looks like. But this is the expert system flagged frame 714 as being a fragment overlap. And now we can see where it is. And that's the reason I needed the next sequence number up there, because it's going to be less than next sequence, but potentially more than the sequence number. So let's see, what does that look like visually? So in frame 699 over here, we pumped out 2,569 stream bytes, starting at that sequence number and going to that sequence number. And then there was a retransmission that we'll look at in a second in frame 714. And that retransmission was 1292 stream bytes, and you can see that it does in fact overlap here with this segment plus some additional bytes on this end. So it is an overlap, but it's also a retransmission. But it didn't get flagged as a retransmission. It got flagged as an overlap. It actually might have gotten flagged both ways. I didn't double check that. I should probably do that. But it did get flagged as an overlap. So this is visually what an overlap looks like. Now the interesting part is, well, geez, we sent 2,569 stream bytes originally, but I'm only resending 1292. And we're going to see that's where large send offload plays a part in a minute, because we're going to compare. So any questions about this? Does this visual help kind of your mind get a picture of what the heck is an overlap anyway? I mean, I had to do that, otherwise I'd have no way to explain it. I couldn't even fully understand it myself. Okay, so I think we've talked about these things. Let's jump over to the client capture to confirm. So here's what we're looking for. This is what came from this is what the server reported on the initial segment send. Now, if we jump over to the client capture, we can see the length field, 1292, 1292, 1292, 1292. What happened to those big segments that left the server, or we thought left the server at that big size? The NIC card chopped them up into smaller packets. And that length probably matches the MTU size that was negotiated at the SYN connection startup. Remember, my client said something like 1360 or 1380, one of those numbers. So we're looking at the client. We can see that smaller packets arrived at the client. So we've definitely confirmed large send offload is enabled. And by the way, it's probably on every modern OS and every modern current TCP stack. If you don't want it on, you'll need to turn it off. So the NIC is handling segmentation. So we've got we see the segment size differences. And let's take a quick look. So we're in the same stream here. Notice that we've got this packet with 52543, and the next sequence should be 522835, which by the one is the one we declared missing. But look what showed up, something farther away, 524112. So if you notice over here, expert info is saying, hey, the previous segment was not captured. So it's letting us know something that we're expecting didn't show up yet. And at this point, we don't really know, was it dropped or was it just out of sequence? And to figure that out, we have to look a little bit farther down. But I need to stop for just a second and just ask, is this magnification useful or is it too much? It's okay? All right, good. All right, so let's look at what comes next. So I just kind of looked at the next few packets on the screen here. So we've got our previous segment is missing, is what it says. What we'd really like is we'd like to see, where's my latest ACK? We would like to see 522835. That's what we're waiting to see. So what comes next is 525404. Still not what we want. And notice we immediately ACK that. and then 526696 comes next, but I'm still needing the one that's missing, which is 522835. So we've gone a little bit further down. It doesn't seem to be out of sequence unless it's really, really out of sequence. It seems to be a drop. And if we go back to our picture at the TCP layer, here's our original segment up here, and then this is what got carved up and sent down to the client. And notice we're missing some stream bytes. And it's actually more, we're missing more than 1292. Notice this says 1292, 1292, 1292. We're actually missing more than that somehow, which is a bit of a mystery. Because so far what we've seen is the NIC card is pumping out 1292 payload size segments. So this is a picture of, hey, here's what we did at the server on the top. Here's what the client received. And oh, by the way, we're missing packets. So how did we get here? We got here because we were investigating fragment overlap on the server, which if you only saw the server side and not the client, you wouldn't necessarily be able to connect the dots of what's happened on the receiver side, right? And part of what I hope happens as you leave these sessions is you start thinking about, okay, here's what I see. This is all I know is what I got in front of me. What's the hypothesis of what could have happened on the other end, either the sender or the receiver? So let's keep going a little bit. We've got some other clues in our little snippet here. This is the same snippet that we had before. So if we go a little bit up in time at packet 1000 here, you know, we sent this first segment at 521543. The next should have been this one, 522835, and we didn't get it, but notice what we did get is the client started ACKing every packet. So when the client starts ACKing every packet, what does that tell you? Well, it was dropped, or they're arriving out of order. It's not the one we're expecting. So it could absolutely have been dropped, and it was in this case. But in our out of sequence class from yesterday, we saw similar conditions with just out of sequence. Okay, so we see a change in ACK behavior, and we talked about why that is. We're going to flip the profile a little bit. Again, same list of packets, but now we've introduced two columns, SAC left edge and SAC right edge, just so that we can actually see what's getting received on the receiver. So we know we're missing the segment that we care about. And you can see the right edge. If we go down the right edge column, you can see it's incrementing, which means we're continuing to receive packets. Because if you think about it, those were sent a while ago from the sender. It took time to get to me. One of them got dropped, but the ones that did not got dropped continued to arrive. So we've got that's why we see packets continuing to arrive, because they were sent a while ago. We're gonna use the visualization technique to get a better idea of what exactly do we mean by a while ago, and what would that look like, because it's hard to see if you're just looking at a packet list. Okay, so I think I just answered this question. I've been rehearsing this a lot, so I'm starting to answer the questions before they come up. Okay, so why does it look like the server's ignoring the fact that we said we're missing something and it keeps sending us things? And the answer is because it's already in flight. It's left San Francisco, it's heading through New York, Chicago, Philadelphia, DC, North Carolina to finally get to me. Okay, so visualization really helps with this. We've got about 15 minutes. And I think that's just about the time that we need. Okay. We've got about 15 minutes before our break for real, before part 2. And I want to use this visualization to help you get a visual clue as to things are happening in both places asynchronously. And this bounce chart really helps you to see that. So it's a little hard to see, but there's a black dot like right there where the mouse pointer is. And there's another black dot down here. Can you guys see that okay? That means I've selected that graphic. And as a result of selecting that graphic, it fills in the decode summary down at the bottom. So now I can see that line is actually 3 acts as in a group that all got sent at the same time. So we've got our rightmost red bar, so we can see packets are leaving right here. They're leaving the server, going up to the client starts to act them, and then you can see the acts come in, the server starts to send more payload, the acts to that payload comes in, and then we send a retransmission out to for the missing segment. So let me there's a few more, like a storyboard here to step through. So here's our friend, the timer, point in time timer. So at this point in time, what's happening? Well, to the left of that point in time, you can see the server transmitted some payload. The blue color says, in the legend here, it carries data. So there's some amount of payload in those packets. So payload is being sent, it's on its way to the client. Client doesn't know anything about this payload yet because it hasn't arrived. Sender knows that it's been sent. Fair enough? Okay. So at this time point, and I'll drill in a little bit so you can see where it is, notice that payload arrived and then it was hard to steady. And then it immediately gets ACKed. In fact, as each payload burst arrives, the client sends an ACK back. And the slope, again, is the time that it's taking. So there's a zoom into that. Now, what's happening at this point in time? And if you, again, split your brain into sender-receiver. So the receiver up at the top, he's ACKed everything that came in. Right? Maybe there's more coming, maybe there's not more coming, I've ACKed it. The sender down at the bottom of the swim lane, has not received the ACKs yet. They're in flight. Does that make sense? So the sender is like, well, I sent some data, I wonder if it ever got there. So we'll fast forward our time a little bit. And now, at this point in time, you can see that this pattern of red came in, blue went out. Why is that? ACK came in, right? I can in-flight data goes down a little bit because I've ACKed some stuff. Now I can send more payload because the congestion window has some room in it. So I'm going to immediately send some more payload. Another red comes in, payload goes out. Third red comes in, payload goes out. Notice I've got 4 reds coming in and 3 blues going out. So why? So the question is, and this is actually a long topic, why don't I have any payload after the last red? So again, let's just zoom in. So I got red, blue, starting from the left, red, blue, and then red with no blue. Well, the red arrives, but I can't send more data because there's an ACK I'm missing. And what we're going to see in a minute is in this red stream, in this red burst here, I've got an ACK with 2 duplicate ACKs. But I don't have that third duplicate ACK that would trigger a fast retransmission. So now I got to wait. I can't send any more data until I hear back from the sender, because he might have gotten the missing segment. So in the meantime, this payload is on its way, right? I guess, can you guys see the white pointer? Right, so I got red 1, blue 1, red 2, blue 2, red 3, blue 3. So I'm sending more payload that's legal to send. But then when I've got that second, the ACK plus the 2 duplicates, I've got to stop sending. I filled up my congestion window, I can't send anymore. And then finally, I think it's here, I just talked about that. So that payload is acknowledged, it's coming in, and part of that group, part of this group here, this red group of ACKs, is the third duplicate ACK. And now once it arrives back at the server, and the order, it really helps you visually, notice that I have a red and a blue and 2 reds. Right, so the first red coming in, red, I'll call that red 1, is where I have my third duplicate ACK. And what happens when I receive that? We send one blue line with an arrow on it. So the arrow means one packet. If there's no arrow, it's a group of packets. And then we flag it as a retransmission of a segment that was missing sooner. So we've got our ACKs coming in. We received our triple duplicate ACK. The payload's on its way. It's a retransmission. And you can see the payload goes up and ACK comes back, and then we can finally resume because everything's put back together again. And I think I have that in the decodes here. So here is it's finally being sent. But notice how the receiver flags, or the expert info flags that segment as out of order. So it kind of gives you a sense of, as the expert info engine is trying to figure things out, it knows it's missing a segment. I mean, I hope it knows it's missing a segment. And here comes something that looks like it's out of order. So it flags it as out of order even though it's a retransmission. Does that make sense? I mean, there's competing labels that you could argue one is right or the other one is right. Okay, I'm going to skip through a couple of these real quick because we're going to take our break. We talked about why is it being flagged as out of order. You know, on the one hand, you might conclude it would really help me if it labeled it as a retransmission, you know, or a fast retransmission. But be aware it's going to get labeled as out of sequence, unless there's a preference for that, which I've not seen. Yeah. Yeah, it's like if you could tweak. So think that, you know, there's a heuristic engine that's making that expert system is a heuristic engine that's trying to make sense of what it sees. And if you could kind of tweak it a little bit, it might be a little more helpful. Okay, so we're all caught up. We've sent the missing segment right here, 522.835. We immediately ACK it. So we're all caught up. Nothing is missing. So here's a question for you. Why do we still send a SAC here? We're actually all caught up. Oh, sorry. Question.
Okay, so the out of order is from the server perspective or from the client perspective?
Great question. So we're looking at the client capture. So this is Wireshark interpreting the client capture. Okay. So my question is, we're all caught up. We've received the missing segment. We've ACKed the missing segment. And my question is, why are the SAC fields populated? And this is not a Wireshark question. This is a TCP question. So why do we think the SAC fields are populated? Say it again. So good answer. I've not heard that term before, but essentially that's what's happening here. We're declaring, oh, by the way, sender, I've already received these 15 bytes. So I've not heard that term. I'm going to have to Google that, duplicate SAC, right? Is that a fairly new? Okay. So we're simply informing the sender, oh, by the way, I've already got these other bytes as well. And if you think about how we started down this path, it was with kind of fragment overlap on the sender side. So we're kind of, our retransmissions are kind of overlapping now because of the large send offload effects, the fact that the NIC is doing some of the work, the TCP stack is doing some of the work. Questions about this so far? And we're about ready to wrap up this session here, I believe. I'm going to skip this for now. The point here was trying to understand what did it cost us in terms of time to deal with this one segment that got dropped. And because there's so much latency in the path, we're looking at, and I think I had it on the previous screen, we're looking at about 119 milliseconds, basically one round trip time. And visually that looks like this here. We sent the ACK, it had to get to California, some payload started to come back, but essentially the delay cost us one round trip time for that one missing segment. And when we go into part 2, we're going to see examples of greater delay caused by similar mechanisms. So I've added to the spreadsheet for the topics that we just talked about, fragment overlap, different frame sizes, display time delta. We had to kind of skip over that slide. And we're finished with part 1. So comments, feedback. Is this an interesting way to think about some complex troubleshooting? Is this helpful? Should I continue on my mission? Anything new that you haven't seen before that you found interesting? The compare and contrast, right? Like, I wonder what's going on at the other end.
I think the way that you present a challenging question about, what is this saying, helps to digest.
So the questions help, right? The leading questions help to hopefully spark the fire.
Because,
Yeah.
we look at the packets and we see something, and you look at the packet and you see something else.
Yes, yeah. Did you guys see the movie The Sixth Sense? I was going to have a screenshot from that with some caption like, I see packet performance issues. Okay, so interpreting behavior can be confusing, complicated, especially with high latency. Sometimes even without high latency, but high latency makes it even worse, even more complicated, because timers start to play a role. Seeing things from both ends is beneficial. Split your brain into sender receiver. Here's the summary of what we looked at in this session. Our Wireshark features are immensely helpful, but they only take you so far, especially when you're trying to get a global view of what's happening on both ends at the same time. And that's where visualizations really help. Advanced analytics are helpful. Thank you for participating. I hope you'll join us after the break. We're just a few minutes early for the break. We'll start back up again at 11. And when we do start back up, we're going to continue straight into bytes in flight, round trip time to ACK, and then we'll have a discussion on congestion. What is it? How is it different than latency? So thank you guys for attending, and I hope we see you at part 2.